We start with a typical optimization problem. We want to find the highest and the lowest values of the function on a certain set. Now, previously, we looked at an open set that was a subset of the xy plane, and we found those local maximums and minimums for all the points that were inside that open set. In the last section, we also found points that were on the borders of that open set by using parametric equations to a function with just one variable. Now we want to find those maximum and minimum values of the function, but we want to use just a curve in the xy plane. So we only have this closed set so that the only xy points that we're considering are the ones that are actually on this curve. And we wish to find the highest z-value and the lowest z-value for all the points on that curve. So now look at the graph. It's going to start and trace around the constraint curve down in the xy plane, and you can see the corresponding point up on the surface at that same time. And we want to find the point on the curve where we're at the lowest z-value and the point on the curve which has the highest z-value. So here we're at the lowest. Now the z's are rising. Right there is where we reach the highest z-value. And so all we're considering is the points on that curve up on the surface that correspond to the points on the curve down on the xy plane. Previously, we found the maximum and minimum values of this function, f, on the set that consisted of the circle with radius 2 and everything inside that circle. So the set, it was a closed set, but it not just included the boundary, but also the region inside of that circle. So we did it two ways. First, we actually used the second derivative test by finding the values, the critical values, where the partial derivatives were both 0, and we found that there was a minimum, a local minimum, at a point inside of that region. Then we had to look at the points that were on the border. The second derivative test only works for the points inside of a region, those open, the points that are inside. So the next thing we had to do was we had to consider the points that were actually on that boundary separately. And so we did that by using the parametric equations to describe the circle, x squared plus y squared equal 4, and substitute into the equation and make it a function with just one variable, theta. So that gave us 2 points. It gave us the smallest point. Now we were just considering the points that were actually on the border. And it gave us 2 points. The one that corresponded to the smallest z-value of those points on the border was located over here, and the point that had the highest z-value that was on that border was located up here. So then if we wanted the absolute maximum minimums, we could consider all 3 of those, the local maximum minimums and the ones for that border, and choose the very highest z-value and the very lowest z-value. Now, looking also at level curves, I pointed out that the level curve, the smallest level curve, was when the z-value was 3, which was at this low point, and that corresponded to this little circle here in the level curve drawing. Each bigger concentric circle corresponded to a larger z-value. And so you can see that if we drew the constraint in blue on that same graph, that constraint intersected several of those level curves. Where it intersected the level curve were points that were on that border, and the largest level curve would be the one that was the largest, where the largest point on that constraint intersected. So this point out here was a point on the constraint that had the largest z-value, the largest level curve value of all of them. Now, the smallest one was right here. So what we want to do is figure out, how do we identify this point and this point What's special about those that distinguish them from every other point on that constraint? Because every point on that constraint does have a corresponding point on the curve and has a certain z-value that goes with each of those level curves values. So this is the where the maximum occurred, and this is the minimum. So that was the smallest level curve and the largest. So now we want to find the maximum or minimum values of a differentiable function f, which is called the objective function. So that function that we're trying to find the maximum and minimum of is the objective function. And we have a restriction on the x and y. They must lie on the constraint curve. So the constraint is that curve that is the border of the set of points in the xy plane. So the constraint will be given as a function of x and y equal to 0. So that's what you're going to be looking for the constraint. The function f is the one you're maximizing. Okay, so now let's figure out what's special about this point here where we actually had that largest z-value of the points that were on the constraint and satisfied the function. Now, what the trick's going to be is looking at the level curves and the gradients. Remember, the gradient is always orthogonal to a tangent vector. So at any point right here on that level curve, the gradient will be orthogonal to the tangent vector. Okay. Now, if we look at the constraint as a level curve also, it ends up that at this point, I mean, it is a level curve. There is a certain z-value there for every point. But at every point, let's look at the gradient. At each point, the gradient is orthogonal to the tangent vector. So at this point, here's our tangent vector and here's our gradient. That's the gradient of the constraint. Now, at that same point, we're also on a level curve. What does the gradient of that level curve look like? Well, the level curve here, this is the tangent vector for it, and the gradient would be here. Well, let's look at the point where we actually have that maximum value. This point is on both the level curve and the constraint. Let's look first at the gradient of the level curve. So in green, the green curve here is what I'm looking at. The tangent vector is here, and the gradient would be here. Now let's change our focus to the constraint. The constraint is the one in red, going like this. The tangent vector at that point would be here, and the gradient is here. Notice that those gradients are going in the same direction. That will be the difference in every other point on that constraint. The places where that maximum and minimum value occurs is going to be where the gradient of the constraint and the gradient for the level curve are in the same direction. Okay, if they're in the same direction, that means they're parallel. Vectors are parallel if they're pointing in the same direction. They just might have different lengths. But what we do know about them is if they're parallel, one of them is a multiple of the other one. So we're going to take the gradient of f, and we're going to find the point AB where that gradient is a multiple of the gradient of the constraint. When we find those points, we'll have our maximum and minimum values. Now let's look at this drawing. I've got all of the gradients for the level curves that are on the points on the constraint and the gradients for the constraint points themselves. So notice here that the green at the starting point, the green is the gradient for the level curve, this level curve, and the red one, well, the red's the tangent vector. The gradient for the constraint is going to be orthogonal to the tangent vector of the constraint. So here's the tangent vector on the constraint, and here would be the gradient. So notice the gradient of the G is not in the same direction as the gradient of the F. So look as this point travels around the constraint curve and find the places where those two gradients are actually pointing in the same direction. They're parallel to each other. We're looking at the green and the blue arrows. They're the two gradients. Right there, that's where the maximum value occurred. And right there is where the minimum value occurred. Those are the only 2 points on that constraint where those two gradients are parallel to each other. Okay, and this is the theorem that states that. Parallel gradients, let f be a differentiable function in a region of R2 that contains the smooth curve C given by g of xy equal to 0. So that's our constraint. Assume that f has a local extreme value at a point on the constraint. Then the gradient of f will be orthogonal to the tangent line at that point. And it follows that there's a real number lambda called the Lagrange multiplier, so that the gradient of f is equal to a multiple, that lambda, times the gradient of g, the constraint. And so that's all this is saying, is that that distance here will be maximized. This is just a picture of a softball field. We're trying to find that greatest distance. It's going to be maximized or minimized at a point here where the tangent vector in the gradient or orthogonal in the level curve is a multiple of that. So let's apply the Lagrange multiplier method. Find the maximum and minimum values of the objective function. So this is what we're trying to optimize. X and Y must lie on the ellipse given by this curve. So we've got a constraint curve. Okay, you can't use the second derivative test and take partial derivatives. It's not going to give you, you don't have an interior points of the set to find local maximum minimums. Local maximum minimums occur inside of a set, not on the border points. So Lagrange multipliers are needed here because the curve, it's an equal here. It's a curve itself. So we want to find the points so that the gradient of f is equal to lambda times the gradient of g. Now remember, the gradient is a vector, and if we have two variables, x and y, it's going to have two components. So let's find the gradient of f. Remember, the gradient of f is equal to the vector that has the two partial derivatives in the components. So the gradient of f will be 4x, partial with respect to x, comma, 2y, partial with respect to y. And we want that to be equal to lambda times, now look at g, you want it equal to 0, so the constraint is in that form, and now find the gradient of g, the partial with respect to x, and the partial with respect to y. Now we want this vector equation to be true. If you multiply lambda through on the right side, you have that 4x must equal to lambda times 2x. That's the first component. And you have 2y must equal to lambda times 8y. Now we've got three variables with only two equations, so we're not going to be able to get unique x, y, and lambdas for that. So this is where the constraint comes in again. We also have an equation that gives us conditions on the x and the y. So that will be our third equation that we're going to use to get unique x, y's, and lambdas. So we want to find x, y, and lambda that satisfy all three of these equations. Now to do that, don't divide through by variables. If you do, you lose answers. So always factor instead of dividing through by variables, and look at one condition first, and then take that condition and combine with the others. So the first one, we have that 4x is equal to 2x lambda. It's tempting to divide by the x, don't do it. 4x minus 2x lambda equal to 0. Factor out 2x. We have 2 minus lambda equal to 0. We have two solutions here. X is 0 or lambda is 2. Now, if you divided by x, you would have lost one of the conditions. Okay. You're trying to find the points x and y. We can take the x equals 0 and actually get the y by just going straight to the third equation. Let's look at the second equation and simplify it a little bit. We have 2y minus 8 lambda y equal to 0, which I could factor to be 2y times 1 minus 4 lambda equal to 0. Okay, now just be careful here because it can get confusing on what to do with all of these. Let's take the two cases, x equals 0 and lambda equal to 2. If x is equal to 0, the second equation doesn't even give us any information. The third equation would tell us that x squared plus 4y squared equal to 4. So that means that 4y squared is equal to 4. So that means y is plus or minus 1. So we have 2 points to consider here, 0, 1 and 0, negative 1. Now case 2. All three of these equations have to be true, so the first one must be true. So either x is 0 or lambda is 2. If lambda is 2, the third equation doesn't give us any information. If lambda is 2, though, we get the second equation would say that 2y times 1 minus 8 is equal to 0. So that means negative 14y is 0. That means that y has to be 0. Well, y equals 0. We don't know anything about x at this point, but we can get the x value by using the third equation. So that means that the x has to be either plus or minus 2. Don't forget, two values here would make that true. Technically, you're taking the square root of both sides. The square root of 4 is positive 2. The square root of a number is always defined to be a positive value, but the square root of x squared is actually the absolute value of x. Look at the definition, and now there's two solutions to this. So that's where the 2 and the minus 2 both come from. So now we have that when y was 0, x is plus or minus 2, so we have two more points, 2, 0, and negative 2, 0. So now let's finish it up here. Look at the 4 points, and let's figure out which one actually gives you that maximum value. So we're going to find the actual value of f. So f of 0, 1, just evaluate up here with the point 0, 1, and you come up with 3. F of 0, negative 1, it's also 3. F of 2, 0 will be 10, and f of negative 2, 0 will be 10. So the maximum value, the maximum of f is 10, occurring at the points 2, 0 and negative 2, 0. And the minimum value of f is 3 at 0 and plus or minus 1. Any other point that's on that constraint, anything else on this ellipse, will have a value somewhere between 3 and 10. So graphically, what we've just found is we're looking at the points on this curve, on this constraint. The points corresponding to those points in the domain are actually the points on this roller coaster. The ones that create the smallest z-values are the points here and here, which are right here and here, and the ones that create the largest z-values are the ones here and here. So let's look at the level curves, okay? If you take different level curves for this paraboloid, you're going to see these concentric circles or concentric ellipses. The smallest level curve is that smallest one in the middle. The largest values for z, where the constraint is crossing, are out here and here. So those correspond to those maximum values. And then the smallest level curve values are here and here. And if you notice, each of these points, if you draw the tangent vector and the gradient for the level curve or for the constraint, they'll all be in the same direction. They may have different lengths, but the tangents are parallel and the gradients are parallel at all four of those points.